For the equilibrium simulation, you're asked to go to this website, Chemical Kinetics and Equilibrium, and use the 3 different tabs that are here after reading the introduction. On the first tab here for kinetics, what you're asked to do is input the percentage of A molecules that are going to convert into B with each step. Step represents time, and the numbers are a representation of the concentration. So I'm going to come over to the left-hand side, use the drop-down menu, and I'll choose 20%. And so in this first box, you're asked to indicate what 20% of 100 is, and that's 20. And then you should be able to either use the Enter or the Tab button to go to the next step. Now you want 20% of 80, which should be 16, and then you press either Enter or Tab, and you keep going. 20% of 64 should be 13 because we can only use whole numbers here. And 20% of 51 should be 10, but I'm going to use some other number and show you what happens if you enter the incorrect value. I'll type in 15, and when I enter that, it says nope, the whole box turns red, and it waits until you get the correct number, in this case 10. Then I'm going to enter that. So as you are doing this, you are asked to input all of the values, and watch what happens in the right-hand side, both for the graph and for the molecules. I'll do this one more time so you can watch them. 20% of 41 should be 8. So watch what happens on the right-hand side as I enter this number. Did you see it? Once you have completed this one, a debrief box will pop open and you should read what the box actually says. You should try 2 or 3 different rates of conversion, one fairly small and one fairly large, and see what the difference is as you do this. Under the Equilibrium tab, now you are asked to input both the rate of A going to B and B going to A. So I'm going to choose still the same 20% for A going to B, but I'm going to choose 50% of B going to A, just because I can do those numbers in my head. And now you have to input 2 different values, one on the left for the percentage of A going to B, and on the right the percentage of B going to A. So 20% of the initial 100 should be 20. Again, use the Tab or Enter button, or click into the other box. 50% of 0 is 0. So when I enter that, it again calculates and graphs and animates what's happening. Now I need 20% of 80, which is 16. And on the other side, I need 50% of 20, which is 10. I'll enter that. And now I need 20% of 74, which should be 15. And 50% of 26 is 13. And then I need 20% of 72, which should be 14. And 50% of 28 is 14. And I need to do this again. 20% of 72 is 14. And 50% of 28 is 14. And now you get both the dynamic equilibrium debrief box, which you want to open, and you're asked to indicate the total number of stable B molecules. That's up here, that's 28. So I'm going to enter 28. And the total number of stable A molecules is 72. The percentage of A going to B is 20, and the percentage of B going to A is 50. And when I enter those numbers, you should see that it doesn't matter whether you use the equilibrium, the rate constants, which are these percentages of change, or the stable equilibrium concentrations of B and A, you get virtually the same equilibrium constant. The reason these are not identical is because the numbers of molecules in the system are so small. You should repeat this equilibrium simulation with A going to be smaller than B going to A going to be larger than B going to A, and another one where the amounts are equal. These percentages of change are equivalent to kinetic rate constant. So notice down at the bottom where we have the equilibrium constant, it doesn't matter whether you calculate it from concentrations or rate constants. The last tab is the Le Chatelier's principle tab. This works just like the equilibrium tab, except that once you reach equilibrium, you can change the numbers of A molecules and or B molecules to anything that you want. There's a total of 130 molecules available. You cannot exceed that. It will not take it. And so try this again. See what happens as you change the numbers in the Le Chatelier's principle box 2 or 3 times, and what happens to the equilibrium position.